Let's try these problems here. This is one. Okay, we want to be able to explain this, and I've actually had students draw a graph like this before on an exam. This is from your textbook, but similar figures also in your reader on page 46. Okay, so first of all, if you look at the two oxygen curves, this is the first two. So there's one here, and there's one here. Those are the two oxygen curves. Okay. Why is the second oxygen curve, the one where my pen is right now, shifted to the right? How do you explain that one? It's merely because it's at higher temperature. So at higher temperature, we have higher kinetic energy, it's going to cause a higher velocity. Also, what you'll notice is a characteristic decrease in the peak height. So the peak will always go down because there's a widening of distributions at higher energy. So to the right, as you go up in temperature, in this example, it's a higher energy, so there's wider distribution. So as it widens, it gets shorter. You always see that happen as it goes to the right. It's wider and shorter. Okay, now let's compare the next curve. So this happened because of temperature, which you could use. You write down this equation. As temperature increases, velocity will increase. Okay, now, this one is at a lower temperature. Why did it shift to the right? The hydrogen curve is also shifted to the right, but it did decrease temperature. Why is that? That's because of the mass. So the molar mass of hydrogen is significantly lower, still causing a shift to the right. So you can see as molar mass goes down, velocity does go up. This molar mass went down so much, oxygen, that'd be 32, versus this would be 2. So it decreased by a factor of 16. But the temperature, let's say from here to here, only decreased by 4. So there would definitely be an increase in velocity. And so that's why this shifts to the right. Again, there's more possible energy distributions, so it gets wider and shorter still. So every time you shift more to the right, you can expect it to get wider and shorter. That's a wider distribution of velocities or energy states. Okay, so that's what that curve is about. Let's go, all explained by this formula, really. Now let's go back to this. We saw this problem at the end of class. Let me just do a quick review of what we've done so far with it, and then we'll continue to finish it. Here's what we did at the end of lecture last time. So this should all be in your notes. First, we did the first question to calculate the ratio. We did that for helium to methane. And for helium to methane, we found that helium is twice as fast. You'd expect that conceptually because helium is lighter. It has a molar mass of 4, where methane is about 16. Okay, then we had to find the root mean square velocity of helium. We did that using the formula you just saw earlier, the root mean square velocity formula, and got 1304. And then we wanted to do the same thing with methane. We used the same formula, the same thing, got 651. Notice a couple things. One is that down here, I have to use kilograms per mole. This is an SI units only question. Or at least that's what I recommend. I think it's easier to only use SI units here. Alright, so these are both in SI units or kilograms per mole. Also notice, these are off by about a factor of 2, which is what we expected from the first calculation. So instead of doing this second bottom calculation here in purple, I could have just taken 1304, plugged it in right here, and do some cross multiplication to solve for CH4 velocity, and basically I'd be dividing 1304 by 2. That would be an alternate way of solving this, the question about velocity of methane. Now let's go on to the kinetic energy. Okay, so we're going to go to the kinetic energy part of the problem. EK squiggly is per mole, kinetic energy per mole. That's typically what we're asking for. There's two formulas, 1/2 mu squared bar, or 3/2 RT. We have two formulas. Just for practice, let's try both. Okay, so it's 1/2 mu squared bar. Really, it's because typically we don't have u squared bar, we have the root mean square velocity. Really, it's most helpful when we typically don't have the mass, we have the molar mass. We're typically going to write this. Okay, so the root mean square velocity squared is u squared bar. And if we actually use the molar mass instead of the mass, it's quite convenient because it puts it per mole. Molar mass is mass per mole, and our answer needs to be in kinetic energy per mole. So it's actually using this formula right here when we do the calculation. It's kind of a variant way of writing the original formula. All right, so let's try that. 1/2 m. And remember, in the previous chapters, capital M is molarity. When you're talking about a gas, we mean capital M is molar mass. Okay? Just following the convention of the textbook. All right, 1/2. Let's just do this for helium. So let me make a little note here. We're doing this for helium. Just to pick one, we have to pick molar mass somehow. It's 0.004003 kilograms per mole. Again, this is another SI units only question. In fact, there's more formulas I would recommend as SI units than ones that I would recommend otherwise. The only one you've seen in this chapter, there's really two that you've seen in this chapter that you don't, I wouldn't recommend SI units. That's the ideal gas law, which we haven't done a calculation with yet. And the other one would be Graham's law. You can go use whatever units you want, as long as they're consistent. Outside of those two formulas, SI units are most convenient. All right, so this times the root mean square velocity, we found that. 1304, it's right above meters per second, and that's squared. Let's see what we get. We get 3403 is what I got, and that'll be in joules per mole. And the energy unit is going to end up shaking out to be joules, and it's per mole because that's EK squiggly. Remember the EK squiggly, the squiggly here means mole. So when you see that squiggly up above the E, that means per mole. All right, let's try this. Now let's use the second formula. Now I want to use this one, 3/2 RT. Let's try that formula. Again for helium, 3/2 are 8.3145 joules per mole Kelvin. And then the temperature is stated in the problem 0 degrees C, and you add 273 to change it to Kelvin. You might remember there's two R's. I definitely have to use this one because I need units of joules, and this is only R that has units of joules. And then the temperature always needs to be in Kelvin. It'll cancel with the Kelvin units that are in R. Let's see what we get. I got 3405 joules per mole. That's convenient because I was calculating the same thing. So I better get the same answer. Okay? Now, what do you think would happen if I did this for methane? I just did this for helium so far. What would happen if I did this for methane? I better get the same answer. For example, look at this formula here. I did not even consider helium in it. I just had a temperature and R and a 3/2. 3/2 and R are constants. and the temperature is not even connected to methane. In this case, I did have molar mass and velocity, but if I put in methane's velocity and molar mass, I'd again get the same answer. Why is that? From the concept that, I think this is bullet 5 or rule 5 of our assumptions. Essentially at the same temperature, temperature is proportional to kinetic energy. What does that mean? At the same temperature, all the gas molecules are going to have the same EK spin. So, because these were both at the same temperature, kinetic energy is the same, I don't need to calculate it for put all molecules in the system. I just need to pick one. So that's why the question, if we go back to the question, said, what is the kinetic energy per mole? And I didn't specify the molecule, because it doesn't matter. It's going to be the same. And in fact, if you use the second formula right here, it really doesn't even matter, because you just need to know the temperature. You don't even care what the molecule is. Okay? It could be any gas whatsoever. So, if you're doing a test, you can pick which formula you use. I tend to prefer the second one, just because there's less variables to calculate. You just need temperature. Everything else is a constant. It's up to you what formula to use, though. Again, I'd recommend the second. I think it's easier. Now, let me say a little bit about units, since we're working with a number. You'll need to know all the following if you don't already. A joule is a Newton meter. A Pascal, which we didn't see in this problem, but just for completeness, this is another one people don't usually know. It's Newton per meter squared. And a Newton is a kilogram meter per second squared. Okay, those are kind of the unusual ones for students. If you don't know those, get comfortable with that. And I would expect you to take units like this, kilograms per mole, meters squared per second squared, and end up with joules per mole. Would anybody like me to do that right now, or is that something you feel okay? Could you get from these units to joules? Who would like me to do something like that right now? Okay. So, if you were doing using this formula, and you wanted to figure out the units, you'd say, well, 1/2 doesn't have units. The molar mass is kilograms per mole. And the velocity is meters per second squared. Let's put that all together. That's a kilogram meters squared per second squared. And then it's per mole. Okay, let me write that another way. That's a kilograms meters per second squared times a meter and then per mole. Why did I do that? Because this right here is a Newton. So now I have a Newton meter per mole. A Newton meter, I know is a joule. So that's joules per mole. And that's how you get units of joules per mole. Okay? So make sure you can do these kind of unit manipulations in order to figure out what your unit should be. Any questions on that? All right, I think I also posted this one. Did I already do this problem before? I can't remember. Doesn't look familiar with airplane pillow? No? Okay. We'll start now, and we have to finish it in a minute. Okay? So, let me explain the concept. Those airplane pillows, if you haven't been on an airplane before, there's the ones that blow up. You can blow them up, and then, it's easy to pack because you can deflate them easily. They fold, but then you can blow them up on the airplane. You have extra pillow, if they run out of pillows, whatever. And so, I want to know when is the optimal time to inflate the pillow. During taxi, which is on the ground, when you're taxiing onto the tarmac, or while you're in the air. So that's the question. We can't answer it yet, but we're going to answer it in a couple minutes, so we'll just leave it kind of floating right there. All right, where are we at? We're in chapter 6. Okay, we're in the middle of chapter 6. I don't think we'll quite finish, but we're going to get close to the end. probably to up to the last section, which in the direction we're going now, we're starting in section 2 and going through 6. So we're doing now the middle part of the chapter. Let's do that. This is section 2. This is gas laws. And just so you can see overall visual of where we're at, put this up for a moment. That's page 42 of the reader again. We did gas properties first, then we did kinetic theory, and you should know kinetic energy, ideal gas law, Graham's law, velocities, and the 5 assumptions. And we did real gases, and now we're going over to the gas laws. We're going to march our way around these. These are some typical gas laws that people derived initially from experiments. So we're going to march our way around the different gas laws, which are in addition to Graham's law. You're going to see the ideal gas law again, etc. Okay, so this is page 48 of the reader at the bottom, and in the textbook, 200, really 201 and following. Okay, we're going to go through a number of gas laws right now. If you took high school chemistry, you probably saw this already. So it might be a little bit of a repeat. That's okay. Boyle's law. The person did some experiments and found the following graph. Plot pressure and volume, found them to be inversely proportional, like y equals 1 over x. Or pressure is proportional to 1 over volume, or we'd also say pressure is inversely proportional to volume. In this case, temperature is kept constant, so we're not worried about temperature. So we can put a proportionality constant, let's say lowercase k is 1 over v, just to make it equal, or to rewrite it, PV equals k. Just a little cross multiplication. And then what's helpful, we can say k, how we usually use the gas laws is comparing two states. So PV at some state 1 or initial state equals P times V at some final state or state 2. And this is typically how we use and what we call Boyle's law. Okay? So we're going to march through a couple different ones of these. There's Boyle's law. Let's go to the next one. Charles' law. Charles' law. Charles did experiments with volume and temperature and found out they're directly proportional, or we might say volume is proportional to T. Now we're keeping pressure constant in this case. So pressure is totally constant. Let's put a proportionality constant in, lowercase k again, just for simplicity. Lowercase k equals capital V over T. But how we typically use it, it's most useful for us, is to compare two states. So how you're going to end up recognizing these problems, and that would be Charles' law, this box right there. You'll recognize these problems because there'll be something's changing. There's more than one state involved. Now, note that temperature has to be in Kelvin here in order to cause this to go through the origin and avoid x or y intercept. Okay, so temperature is in Kelvin. Okay, next. Let's do Avogadro's law next. Okay, Avogadro did some similar experiments. In this case, volume in moles. Lowercase n is moles. Found out they are directly proportional, or volume is proportional to moles. Or to put in, again, a proportionality constant to make it equal, so we can have a formula that we can mess around with. So K is volume over moles, or if we make what's called Avogadro's law, again comparing two states, it would look like this. In this case, pressure and temperature, all that is constant.
Question.
Now, yeah.
How is it possible, like if you have a balloon, for example, and you have like a gas in the balloon, then, but you like put more, you make the balloon bigger somehow or something, but that doesn't necessarily increase the amount of moles that are in it, though, right? Like,
That's right. So she's saying if you have a balloon, if the balloon gets bigger, would the moles necessarily change? No, but in that case, moles would be constant. So this would be a different kind of experiment. This would be where you have a balloon or something expandable, and you have an inlet, and you're adding moles. Well, you expect if you add moles to the inlet, you know, the moles are going to go in and cause the volume to increase because there's more on the inside.
so it's only possible for it to be one way, like you have to add volume and then the moles will increase. You can't, no, you have to add moles and then the volume and it will increase. You can't just add volume and then the moles will increase.
Oh, she's asking, does it work the other way around? Well, if everything else is constant and moles are able to increase or decrease, if you have a set pressure and moles are freely able to go in, if you increase the volume in order to compensate for that increase in volume, moles would have to go in. Otherwise, the volume wouldn't be able to go up.
But doesn't that violate the law of conservation of mass?
That wouldn't violate the law of conservation of mass if moles are allowed to freely go in or out.
Oh, but you have to allow that freedom.
You have to allow the moles to go in or out.
Oh.
Because moles in this case are changeable. So the moles are a variable in this case. And since you bring that up, let's mention a couple of the ones that we've done already. So hopefully it does make intuitive sense that if you add moles, the volume should go up because there's more in there. Or, for Charles' law, as you increase the temperature, things are going to move around more. And to keep the pressure constant, because the pressure would want to go up, keep the pressure constant, you need to increase the volume. So that's why, that's to explain Charles' law, as you increase the temperature, the volume has to go up. And then the original one that we just did, pressure and volume, if you increase the volume, the pressure has to go down. There's less, you know, the number of moles is not increasing, so if you make the volume bigger, the pressure has to go down in order to compensate. Okay, so you can think of these like you were asking, very conceptually, and they should make sense. Okay, let's kind of scoot back here. Now, there's a little more to say before we go on to the next law. Let's talk about Avogadros for a second. There's something called STP, you might have heard about before. It stands for standard temperature and pressure. Standard temperature and pressure. The standard temperature is 273 Kelvin, and the standard pressure, just by definition, is 1 bar. Okay? Why that's interesting, and using ideal gas law, you could actually do this kind of calculation. You can find out that 1 mole of a substance, if it's an ideal gas, following the kinetic theory of gases, this would occupy 22.7 liters. Okay? So this is a nice conversion ratio, because now we know that 22.7 liters per mole is a ratio of conversion. For any ideal gas, and this is the mole volume comparison that can come out of Avogadro's law. So let me say a couple things about this. First of all, if we go back, I know we haven't seen this for a little bit. I'll go back to the notes in a moment. Here, you vaguely remember the molar express. And now, to go between moles and volume, there's 2 ways. If you're talking about a liquid, Chapter 4 material, molarity is a conversion to go between moles and volume. If you're talking about a gas, then 22.7 liters per mole is the way to convert back and forth between volume and molarity. So we have a new pathway of sorts to go between volume and moles using that ratio that kind of trickles out of Avogadro's law. Okay, I need to say something else about this though. Unfortunately, I've been teaching this class for a long time, and over time, the standard pressure has morphed. So let's change colors here. Old standard pressure was 1 atmosphere. That meant that 1 mole was about a little less than 2% different. Instead of 22.7, it was 22.4 liters per mole. In previous classes, who has learned this one? The old one. Okay, that's common. That's what I learned. That's what I used to teach. But we've has morphed into 1 bar now. So now we have to use the 22.7. If you look at even some of my old exams, you'll see me using 22.4. Just know it's 22.7 now. Okay, so that's what I expect you to use. And/or if I say standard temperature and pressure, and you need to use a pressure, you should be using 1 bar. Okay? So know that difference in the case that you used to use this old conversion. Okay? If you didn't, never heard of it before, even better, just know the new one. Okay? This is standard temperature and pressure, and this is a conversion that you can use to go between volume and moles. All right. Let's take a look at the airplane pillow again for a moment. Okay. What's lower pressure on taxiing on the ground or up in the air? Up in the air, right? Does that make sense? Okay, if you didn't know that, yes, sea level is atmospheric pressure. You decrease in pressure, less gas as you go to the outer atmosphere, and so slightly less pressure as you go up. Fair enough? Okay, so less pressure as you go up into the air. Let's say I filled up my airplane pillow on the ground, as I go up in the air, if pressure is decreasing, what's going to happen to the volume? Now, it's going to go up according to what law? Boyle's law. As pressure goes down, volume will go up. So if you inflate your pillow, you know you got to mess with your hands and stuff. You can't perfectly get it full. That's okay, because if you inflate your airplane pillow on the ground, it'll be fully firm and taut up in the air. So I would say the ideal place to fill up your balloon or your airplane pillow is on the ground. That's when you get up into the air, it'll be a nice firm pillow to sleep on. If you fill it up while you're up there, you're going to get this lumpy pillow because it's hard to totally fill up those kind of pillows. So I was telling my wife, we've got to get your airplane pillow out. We must fill it up during taxi or I will be uncomfortable. Okay, there we go. Learn about life, don't you? Okay, next. One more law in section 2 before we go on to section 3, really, that I want to mention. I'm not going to say much about it, just mention it. This is the Gay-Lussac law, kind of along the same lines. And this comes up with this initial to final state formula. So let's see, how many was that? That should be 4 that you have written down right now. Okay? And this leads us into section 3. To the 5th, should be at this point from section 2 at least, now into section 3. Continue. To the 5th law. What I'm going to do is take a look at the other 4 laws, and I want to put them with respect to volume. So for example, if you take a look at Boyle's law, you get this. If you take a look at Charles' law, you should get this. And if you take a look, let's see, which other one has volume? Avogadro's law. And I think that's about it. Okay, what you can do is take all of these, we get a different pen color now. volume is now proportional to, since it's proportional to, you can just stick all these things together, N T over P. Let's move that around a little bit. PV is proportional to NT. Hey, let's get rid of the proportionality. PV, let's pick a random proportionality constant. We'll call it R, and for some reason we'll put it between N and T. There we go. Here's our ideal gas law again, which can also come as these other laws from experiment. So earlier, when we did kinetic theory, we derived it, okay? Except for R. R comes experimentally. But you can also kind of, through this sort of motion of the other proportionalities we know, you can also trickle out, shake out this ideal gas law. So again, this is the ideal gas law. The R you want to use here that I recommend is this one. Mostly out of convenience. It has, instead of joules in the numerator as the unit, it has liters in atmosphere. Liters fit well with the units of volume, liters. And atmospheres go well with the units of pressure, atmospheres. And so I see this one to tend to be the most convenient R unit to use. Now, how do you know when to use which unit? I'll get you in a second. How do you know when to use which unit? Pretty much you're going to use this R only for the ideal gas law or its kind of derivatives, similar gas laws that are derived from it. But for anything else, you're going to use the other R because that has SI units and that's going to tend to be most convenient. Okay, so this R for the ideal gas law or its variance, and the other R for pretty much everything else.
So if you're given gas, you're going to convert from bars to atmospheres.
You got it. So what he's saying, what if you were given a gas at STP, what do you do? To use this, I would convert the pressure of one bar into atmospheres and then use this law. Okay? So yeah, again, if you're given STP, that pressure is in bars, change that to atmospheres, then use this. Okay? And this law. That'd be my recommendation. Of course, there is R in liters bar per mole Kelvin. If you happen to know that one, memorize it, whatever you can. I'll give you these R's, though, that I've shown in class on the exam, which you can see when you look in the practice exam, first couple pages, has the exam 2 units on there. Okay, hope that all kind of made sense. Now we've gone through the gas laws. I want to say kind of couple more things before we do some examples. First, there can be variations of the ideal gas law. Let me show you. What you'll see pop up from time to time is occasionally we'll put in a problem density, just to annoy you. And you know that's mass over volume from chapter 1. Or to be super annoying, we'll toss in molarity. Not molarity, it can't be molarity, that's chapter 4. Molar mass. Molar mass would be, we know this, mass, grams, over moles. So what happens commonly in an ideal gas law problem, we toss these these variables in there, or as givens, and we say, okay, you have to use the ideal gas law to solve for something like the temperature or whatever. So what you need to realize is that you can substitute these three formulas into each other however you want to, and they easily substitute into each other because volume is here and here. You got moles here and here, so it's easy to put these into each other. For example, just as one possibility, let me show you how it could work. You could say, well, volume is mass over density, so then pressure times mass over density equals nRT. For example, if you need to put density in this formula, that would be a way to do it. You could, if you wanted to, mess with this one, and I'm just doing it randomly, it just depends what you are given and what you need. You could say, well, pressure, let's move everything over. Pressure is equal to nRT over m times d. Just kind of cross multiply. What's n over m? N over m. It's going to be 1 over the molar mass. N. So you can substitute RT, it's about the density in the over molar mass, just as another variant. So there's a lot of ways you can put these formulas together if you want to. The key is starting to where I have it boxed. Okay? And you can substitute them depending on whatever you're given in a question, and you'll see us do an example a little bit. Okay, one more law for this section. It's called the combined, that's a B, combined gas law. Sometimes it's also called the general gas law. So combined or general gas law. It's where basically if you take the ideal gas law, solve for R, it's PV over RT. And just like before, if you remember, we took the proportionality constant, that's R, and solve for it, and then put state 1. Oh, why did I put an R down there? This should be an M. State 1, and this equals PV over NT state 2. This is called the combined or general gas law. It's basically Boyle's, Charles, Gay-Lussac, Avogadro's all together into one law. I tend to, instead of having to remember which one's Boyle's, which one's Charles, I get a little confused. I just remember if I solve for R with the ideal gas law, I immediately have out the combined gas law, and I just use the variables I need. Okay? And you'll see us do an example like this in a moment. That's the combined gas law. So, how to solve problems? I ask myself a simple question. Is there some initial to final state change? So is the states, is volume changing, is pressure changing, anything changing? That's a question I ask when I'm doing a gas law. And really, it's yes or no. If no, if there's no change, use the ideal gas law to solve it. Okay? Ideal gas law is not involved with changing temperature or pressure or anything like that. It's a set for one state. If yes, then use Boyle's or Charles or Avogadro's, or if you're me, I just remember the combined gas law because it has all of them stuck into one. Now you might ask, well, what do I do if moles aren't changing, for example? Well, what if something's not changing because the combined gas law has all four things changing at the same time? Well, if you have something that's not changing, like moles, for example, you just erase it. How can you just erase something, you might ask? Well, if it's constant, it's equal on both sides, and so it drops out of the equation. So anything that's constant or not changing, you drop out of the combined gas law. And we either will state that clearly in the question, hey, this is constant, or if we don't state it, we're assuming that it is constant. Okay, so if it's not stated, assume that that variable is constant, or obviously if it's stated, assume it's constant.